So, now let us see the implementation of TLBO on MATLAB. Right. Before we start looking at the code of MATLAB, we will have to know some basic functions. Some of you might already be knowing this, but for those of you who do not know, let us just quickly see some of the basic functions. So, if you recollect, we will be using random numbers multiple times, right. So, the function to generate random number in MATLAB is rand. So, if we give rand, it is going to give us random number between 0 and 1, right. So, if we want let us say 10 random numbers, 1 row 10 columns. So, we can give rand of 1 comma 10. So, this will give us 1 row and 10 columns of random numbers between 0 and 1, right. So, another function that we will be using is randi. So, remember that for selecting the teaching factor, the teaching factor has to be either 1 or 2, it has to be randomly selected. We can either use this rand function to generate a random integer, or we can directly use this randi function, right. So, the syntax for randi function, if we require random numbers between let us say 1 and 50, right, 1 and 50, and let us say we require only one variable. So, what we are saying is between the number 1 and 50, right, give us 1 row 1 column, that is we are looking for a scalar. So, this will give us a random integer between 1 and 50, right. So, if we keep generating it, we will obviously get different values, right. So, for us in our case, let me just clear the screen. In our case, we require random number which has to be either 1 or 2. So, right, I can give this. So, this will give us random number which is a random integer which is either 1 or 2, right. So, now we know how to generate random integers and how to generate random numbers between 0 and 1. However, when we generate our initial population, the random number has to be between a lower bound and upper bound, right. So, let me say my lower bound is 5 and the upper bound is let us say 10. So, now we are looking to generate a random number, not necessarily an integer, right, between 5 and 10. So, we can use this relation LB plus UB minus LB into a random number, right. So, this will give us a random number between 5 and 10. So, UB minus LB is a positive quantity, right, and random number is between 0 and 1. So, the second term is always going to be a positive. So, since we are adding it to LB, this number whatever we will get will be greater than lower bound. Similarly, you can analyze that whatever number we will get from this relation will always be lower than upper bound, right, lower than upper bound or equal to upper bound, right. Let me clear the screen. So, the same relation we can use over vectors also. So, let us say I have 3 decision variables, the lower bound is 379, the upper bound is let us say 5, 8, 10, right. So, now still we can use the same relation, right. Now, we require 3 random numbers because we have 3 decision variables, right, and we will do a element by element multiplication. The first value will always be between 3 and 5, the second value will always be between 7 and 8, and the third value will always be between 9 and 10, right. So, this is how we will be generating our initial population, right. So, there is another useful function in MATLAB called as repmat, right. So, obviously for all these functions you can just go and type help the name of the function to further read it, right. Here we are quickly showing you how to use this function. So, for example, now that I have this lower bound, let us say I want to replicate this lower bound multiple times. So, I can use this function rep mat LB comma 5 times I want to replicate it, right. So, 5 comma 1 will give us the same row replicated 5 times. So, if we give 5 comma 2, right. So, our lower bound was 379. So, 379 has been replicated as shown over here, right. There are 5 rows and 2 blocks of what you can consider as 2 blocks of those columns. So, we can use this repmat function to generate the initial population. Apart from that, we will have to locate the minimum of the function. Let us see, given a vector, let us say x is equal to right. So, if this is the vector, right. So, if I want to locate the minimum value of this vector, so I can just give min of x, right. So, min of x will tell us the minimum value in this vector, right. However, we are not only interested in the minimum value, we are also located in the location of the minimum value, because remember we will identify the teacher from the fitness function value, but we will also need the teacher which has to be extracted from the population, right. So, we were using two different variables, one for population, one for fitness function value. So, first we will have to locate the minimum value, and then correspondingly we will have to extract that set of decision variable from the population, right. So, now we are also interested in the location of it, right. So, if we want to identify the location of it, we can do this val comma int, right. So, these are two variable names that I am specifying. You can specify any other name, right. So, if I do min of x now, I will get the value, minimum value in the first variable, that is val, and the location in the second variable ind, right. So, ind, I used ind to denote its index, you could have used any other variable name, right. So, it now says that the minimum value in the vector x is 4 and it is located at the first position. So, let us try it at some other vector where the minimum value is not at the first location. So, we have revised the x, and if we do this again, so now it says the minimum value is 1, right, out 5 7 8 1 5, the minimum value is 1, and the index, that is the position that it is located, is the fourth location, right. So, that way we can identify the teacher and as well as extract the appropriate member, right. So, if I have this matrix, let us say some random matrix of 3 rows and 3 columns. If I want to extract the second row, we can just give a of 2 comma colon. So, this will extract the entire second row. Similarly, if you want to extract a particular column, we can say all rows of, let us say, the third column, right. So, this way we will be extracting the teacher from the population member. So, let me just clear this screen command window. I have this variable a, right. So, if I say mean of a, right. So, remember in teaching learning based optimization, we will also be required to find out the mean of the population. So, we will be using this function mean over there, right. So, mean of a will give us the mean for every individual column. So, the mean of 5 8 7 is 6.66, 7 10 8 is 8.33, 8 17 19 is 11.33. So, this is a function which we will use to find the mean of the population, right. So, one more important operation that we will require in TLBO is the bounding of the decision variables, right, the corner bounding strategy, that if a variable is violating the lower bound, we will have to move the value to the lower bound, and if a value of a variable happens to violate the upper bound, we will have to move the value to the upper bound. So, obviously, we can implement a if condition and then check whether it is violating or not, or we can use the max and min function. So, we will just see how to use the max and min function to implement the corner bounding strategy. So, let us take lower bound to be, let us say, 5 8 and 15. So, I have 3 variables, the lower bound is 5 8 15, right. Let my upper bound be let us say 50, 90 and 100. So, I have 3 variables, the upper bound of them are 50, 90 and 100 respectively. Let us say I get a solution somewhere which is let us say 1, 7 and 95. Right. So, this if we see, first let us just check with the lower bound. So, the first variable violates its lower bound because the lower bound is 5, the value that we have is 1. The second variable, the lower bound is 8 and the value that we have is 7, right. So, these two variables have to be corner bounded. The third variable is within the domain, right. So, the lower bound is 15, the value that we have is 95. So, it is not violating the lower bound. So, what I can do is that my new x is max of my x comma lower bound. So, what it will do is it will compare 1 and 5, right. It will do element to element comparison, whatever is maximum will be retained. So, in this case 5 is retained, between 7 and 8, 8 will be retained, between 95 and 15, 95 will be retained, right. So, which is what we want. So, this is our corner bounding, this is our new solution which has taken care about the violation in the lower bound. Similarly, I can take care of the violation in upper bound. So, let us say the upper bound for the first variable is 50, so let us say it is 45, so it is not violating. The upper bound for the second variable is 90, let us say it is what I get is 98, and for the third variable let us say it is 120. Right. So, now I have this new solution 45, 98, 120, and the upper bound of this are 50, 90 and 100, right. So, now if I want to implement the corner bounding strategy, just like this max of LB, I can do x is equal to min of x comma UB, right. So, it will compare this 45 to 50, right. So, 45 is less than 50, so it will be retained. Since it is not violating the upper bound, the value is being retained. 98, if we see, it is actually violating the upper bound, right. The upper bound is 90 and the value that we have is 98, right. So, it is violating the upper bound. So, min of 90 comma 98 will be 90. So, the value of that particular variable will be replaced with 90, and similarly the third solution is also, the third variable is also violating the upper bound, right. The upper bound is 100 and what we have is 120. Right. So, what we will do is minimum of 100 comma 120 will be 100, right. So, if we execute this, whichever variable is violating the upper bound, it will be brought back to its original upper bound, right. So, this is also something that we will be using while we are implementing the TLBO algorithm. So, I guess as of now we are ready with whatever the functions which we are going to use, right. So, let us look at the code of TLBO. Rather than coding in real time, we thought like we would be able to save some time if we already have it coded and then walk you through the code line by line, right. So, this is the code in the editor, what you say is the code of teaching learning based optimization, right. So, the first line is CLC, right. So, first what we will do is we will just browse you through the code and then subsequently we will come through this code again in a debugging mode. So, we will be able to better understand. So, what we are doing first is clearing the command window using the CLC command, right, and then we do not need any of the variables which are already defined in the workspace. So, we are clearing the workspace with the clear command, right, and then we need to define the problem that we are going to solve, right. So, right now we have taken a 2 variable problem whose lower bounds are 0 0 and the upper bound are 10 10. The problem that we are going to solve is, we have written that in a function file. We hope that you know what is a function file. So, the name of the function file is peernew, right. So, we have assigned that function to this name prob. So, prob is now a function handle because it is defined with this @ symbol, right. So, peernew is a function, we will look into that function, what is that function. So, we include this function handle because we wanted to write a generic function, right. So, we have included it as a function handle. Now, let us just look into peernew, right. So, peernew is the objective function file, right. So, here we expect that whenever this file is called, we are given decision variable, right. If there are 2 decision variable, let us say x1 and x2, it will do summation of x1 square plus x2 square. So, this x dot the power 2 will square each element and then the sum will sum the entire vector, right. So, that way this objective function is independent of the dimension. So, instead of 2 variable, if we send 10 variable, right. So, it will square each element using this part and then it will sum all of that, right. So, this is the peer function and it will return the fitness function value, right. So, that is what this peernew function will be doing for us, right. So, these 3 lines complete the definition of the problem. So, remember, for most meta heuristic techniques, what we require from the problem definition is the lower bound, the upper bound and a procedure to evaluate the fitness function. Now, that is done, we will have to define the parameters related to the algorithm. So, TLBO, as you know, has 2 tuning parameters. One is the population size. So, we are using the variable NP to indicate the population size. So, initially we have taken a population size of 10 and we want to perform 50 iterations. Since we are doing it on a computer, we will be able to perform 50 iterations fairly quickly. So, this is what is the algorithm parameters. So, with this line, whatever was required to execute TLBO has been defined, right. So, it has been defined in the very beginning itself. So, the rest of the code is generic, it will be using values from here. So, since we have NP population members, we are defining a variable f with the values as NaN, how many values of NaN will be there in F depends upon this NP. Since we are going to store the fitness function of every member, we have defined F with NaN values and it has a dimension of NP rows and 1 column, right. So, that will give us a vector F which will have NP elements. It will be a column vector, it will have NP rows, right. Right now we have not evaluated the fitness function, so we are storing NaN into these values. As and when we evaluate the fitness, we will plug in the corresponding values, right. So, since we do not know the dimension of the problem, right, we determine the dimension of the problem by taking the length of LB. So, if LB has 10 values, D will become 10. So, this length is an inbuilt function of MATLAB which will tell us the number of elements present in the lower bound. So, for every decision variable we will have a lower bound, we will have to have a lower bound and an upper bound, right. So, by measuring this length of the lower bound, we can find out the number of decision variables, right. So, the next step is to generate the initial population, right. So, to generate initial population we use the repmat function, right. So, this part will replicate the lower bound NP times, right. So, this is the same relation which we have used LB plus UB minus LB into RAND, right. It is just that we are generating the entire population in one line. So, that is why we have used this repmat function, right. Repmat LB will be repeated NP comma 1 times, right. So, basically it is going to replicate the LB row multiple NP times, right. This UB minus LB, so the range between the upper and lower bound, the range will be replicated because of this repmat will be replicated NP cross 1 times, right. And then for each population member and for each decision variable we require a random number which is between 0 and 1. So, that is why we have this rand of NP comma D. So, since NP is 10 and D is 2, it will give a 10 cross 2 matrix, right. So, we can just try it out, rand of 10 comma 2 if we give, right. So, it is going to give us 10 rows and 2 columns, all the values will be between 0 and 1, right. And then we perform a element to element multiplication to determine the population. So, we have chose to determine population in this way. You could have if you are working with some other language which does not have this repmat function, you could have write 2 loops. So, you can say for I is equal to 1 to NP, for j is equal to 1 to D, P of I comma j is equal to LB of j plus UB of j minus LB of j multiplied by a random number, and then execute that loop twice, so that we will be able to get the population. So, since MATLAB has these very useful functions, it becomes a little bit easier to generate them without necessarily using for loop. So, once we have created the initial population over here, the next step is to evaluate its fitness, right. So, to evaluate its fitness, we can either call the function spearnew or we can use this variable PROB, right. So, we will use this variable PROB everywhere, so that if we have to solve some other problem, we merely need to define the new problem in line 7. We do not need to individually figure out the calling of the function and replace it. That is why we chose to have a function handle, right. So, now what we are doing over here is we are sending the member one by one to the spear function using this prop variable, and we are receiving its fitness value, right. So, this loop will be executed 10 times NP times, because we need to determine the fitness of each member, right. So, f of 1, f of 2, f of 3, it will go all the way up to 10, and every time when we are calling prop function, we are sending the pth member of the population. So, first time we will be sending the first row all the columns, because remember for us an entire row constitutes one solution. If there are 10 variables, the first row and all the 10 columns will constitute the first solution. So, we need to send the entire solution to evaluate the fitness function, right. So, this loop will help us to determine the fitness of the initial population, right. So, these 3 steps these 4 steps are going to be common across all meta heuristic techniques that we are going to discuss as part of this course, right. We will have an initial population which we will generate randomly between the upper and lower bounds and evaluate its fitness, right. Here we have chose to send the population member one by one, right. But if you modify this objective function appropriately, then we could have sent all the members together and could have received all the fitness functions together, but to begin with, we have not taken a vectorized function. This function is capable of receiving one member at a time and returning the fitness of one member at a time. If this function is appropriately modified, we could have sent all the population members and received the objective function values in without the use of this for loop, right. So, that completes the initialization part, right. So, we have generated the initial population and evaluated its fitness, right. Then begins the iteration loop of TLBO. So, now we need to do something repeatedly for t times, right. What we are going to do repeatedly for t times, that is what we discussed in the previous session, that we will execute the, for each member we will execute the teacher phase, and for each member we will execute the learner phase, right. So, we define this exterior loop for t is equal to 1 to t, right. So, that loop is ending in this line 77, right, from line 25 to 77, whatever is between the line 25 and 77 will be executed for t times, right. So, then we have to, for in each iteration, each member of the population is supposed to undergo the teacher phase as well as the learner phase. So, we again use this for loop at line 27, right. So, 27, that for loop is getting over at 74. So, whatever is between line 27 and 74 will be executed for NP times, right, and whatever is between line 25 and line 77 will be executed for t times, right. So, we have these two loops. So, the outer iteration loop and the inner population loop, right. So, now that we have set the loops in motion, the next step is to implement the steps of teacher phase, right. So, in teaching learning based optimization, the way we discussed was the first member undergoes teacher phase and then the subsequent member undergoes the learner phase, right. So, for the first member to undergo teacher phase, we need to find out the mean of the population. So, mean function we have seen few minutes back, right. So, if we give mean of p, p is our population. So, it will give us a row vector which we are assigning to the variable x mean, right. So, x mean will contain the mean of the population, right, and then at line 31 we are determining the minimum value of f, right. We are not interested in the minimum value of f, but what we are interested is in the location of it, right, because to extract the teacher we need to know the location, right. So, that is why we are not receiving the first value, right, we have put a tilde symbol over there, and but we find out the index, the location of it, right. So, now this is the location, IND will tell us the location wherein the minimum value of f is present, right. So, once we have that, from the population we need to extract that particular solution. So, we had discussed how to extract a particular solution, right. So, what we are doing is p, because the members are stored in population p. So, for p we are extracting the corresponding row indicated by the variable IND, right, and all the columns, because that constitutes the entire solution. So, now we have determined x mean and x best, right. The next step to in order to employ teaching learning based optimization is to have a teaching factor. So, as we have discussed earlier, irrespective of any number of variable, teaching factor is constant for all the decision variables. So, here we make use of the randi function which we discussed to generate a random number which has to be 1 or 2, right. This 1 comma 1 make sure that we get only one value. So, that is stored in this variable TF, right. So, to generate the new solution, we have all the required values, right. So, we want the best value, the best member, the mean of the population, teaching factor, and the current member. So, the current member we can extract of p of I comma colon, I because it is the ith member which is currently undergoing the teacher phase. So, our new solution is going to be p of I comma colon. So, the current solution plus rand of 1 comma d, because there are d decision variables, we are generating d random numbers, right. So, we will get a row vector over here, that we are doing elemental multiplication with this term, which is the difference of the best and the mean with the teaching factor incorporated, right. So, this is the equation which we had seen while we were learning teaching learning based optimization. So, this will give us our new solution, right. So, this new solution may or may not be in the bounds, right. So, we need to bound it, right. So, in order to bound it, as we had discussed in the beginning of this lecture, what we will do is we will use this function min of ub comma x new, right. So, if it happens that the member is violating the upper bound, right, since we are let us say we have 5 comma 10, let us say u b is 5 and x nu is 10, right. So, min of 5 comma 10 will be 5, right. So, that way we are pushing it to corner boundary. So, line 38 takes care that the newly generated solution is brought back to the upper bound if it violates, right. If it is not violating, it will not have any impact. Similarly, in line 39 we are making sure that the solution the variables which are violating the lower bound are brought back to the lower bound. So, line 38 and 39 will ensure that the solution is bounded. Now that the solution is bounded, the next step is to determine the fitness function of it, right. We need to determine the fitness function of the newly generated solution, because we need to subsequently employ a greedy selection strategy. So, in the greedy selection strategy, we will have to compare the solution of the current member which is undergoing the teacher phase and the fitness function value of the newly generated solution. So, whichever is better will survive, right. So, we need to find out the fitness function of the newly generated solution. So, f nu is the value of the fitness of the newly generated solution. Prob, as we know, contains the fitness function which we are trying to minimize, right. So, we are sending this newly generated solution to this prob. So, then this prob actually indicates the sphere function. So, this x nu is sent to the sphere function, it is evaluated and the fitness is stored in f nu. Right. So, now we are ready to implement the greedy selection strategy. In the greedy selection strategy, we are employing this if loop in line 43, right. So, f nu is the fitness of the newly generated solution and f I is the fitness of the ith solution which is undergoing the teacher phase, right. So, if f nu happens to be less than f of I, that is we are solving a minimization problem, right. So, since we are solving a minimization problem, a better fitness is the one which has the lower fitness is better, right. So, if this condition is satisfied, then we are overwriting the ith row of the population, right. So, we are overwriting the ith row of the population using the newly generated solution x nu. Once we have overwritten that, we also need to overwrite the fitness function value. So, since the ith member has been replaced with a new solution, we need to replace the fitness function of the ith solution with the fitness function value corresponding to this new solution x nu, right. So, this line 43, 44, 45, 46 employs the greedy selection strategy and includes the new member if it is better, right. If condition is not valid, then the new solution is not used, right. This overwriting will not happen, that way the ith solution survives it. That completes the teacher phase, right. So, now we will implement the learner phase. So, to implement the learner phase, we need a random partner, right. So, what we are doing is we are again using the function randi, right. Now, this time we want a random number which is between 1 to the population size. So, if you have 10 members, we need a random number which is between 1 and 10, right. So, again 1 and 10 included, right. So, we give this randi of 1 to np within the square bracket, and for each member we are going to generate a partner, right. So, for the ith member we just need one partner. So, we give this 1 row comma 1 column. So, this p will return us one value, one integer value which is between 1 and np, right. So, it might happen we are getting the value of p to be the same as the value of I, right. It can happen. So, what we are doing is we are implementing this while loop, that if I and p are equal. So, let us say if the fifth member is undergoing the learner phase and the partner is also happens to be 5, right. That can happen because we are generating a random number between 1 to population size and the random number generated could also be 5. So, the fifth member is undergoing the learner phase and line 51 may give us p equal to 5. So, it is like fifth member is the partner of fifth member, right. So, we want to avoid it. So, we have this while loop. So, if this condition happens, then we generate another random number. So, this while loop will ensure that we get a partner which is not equal to I, right. So, now that we have selected the partner, the next step is to generate a new solution. In the learner phase, there were two equations, right. So, depending upon the fitness of the partner and the fitness of the solution which is undergoing the learner phase, the appropriate equation has to be used. So, here we implement the if condition, we check that if f of I is less than f of p, then we generate the new solution using this equation, right, else we generate the new solution using this equation. So, this equation, if you remember, the new solution generated in the learner phase is the current solution, which is P of I comma colon, right, colon because we are taking the entire solution, plus the difference between the ith member and the partner multiplied by a random number which is between 0 and 1. So, again here we will have to generate d random numbers because we have d decision variables, right. So, this x new will give us a new solution. Again we need to bound the solution. So, we will skip the explanation of this because we have explained it earlier, right. This is exactly similar to what we did in teacher phase, that we are ensuring that if the lower bound is violated, the variable is brought back to the lower bound, and if the variable is violating the upper bound, the value of the variable is brought back to the upper bound. So, at the end of line 65 we have now generated a solution which is within the bounds, right. So, once we have generated a feasible solution or a bounded solution, we need to evaluate the fitness function value. So, that is done in line 67. So, in line 67 we are again evaluating the fitness of the newly generated solution. So, now after evaluating the fitness of the newly generated solution, we again employ a greedy selection strategy in line 69 to 72. So, if the new solution happens to be better than the current member, it is taken inside the population and its fitness function is also taken inside the population, right, else the ith member is retained, it is not overwritten and it is retained. So, this completes the learner phase. So, we have an exterior iteration loop and then we have a population loop, and inside the population loop we have implemented teacher phase and learner phase. So, every member will first undergo teacher phase, it will complete learner phase, right, and then the second member will undergo teacher phase and the second member will undergo the learner phase. So, this is going to happen for all the population members and this entire procedure is going to be repeated t times, right. So, that is the implementation of TLBO. As you can see, it is a fairly simple code that we can implement. So, TLBO, as we had mentioned earlier, TLBO is not an inbuilt function in MATLAB. So, we can quickly develop this code and then we can use it, right. So, let us say we have executed the TLBO. So, what is that we are interested in after execution, right? We are looking for the best fitness, right. So, since we have this in line 79, we find the best solution. When we reach line 79, the TLBO procedure is over, right. So, now we have a population at the end of TLBO, we have a population and a fitness f. We are locating the minimum value. We are storing the value in best fitness, in the variable best fitness, and we also require its location, the location where the best value is present, right. And then again we extract the population member corresponding to the best fitness. So, that we are calling it as best sol. So, this best fitness and best sol is what we are interested in. Best sol indicates what are the decision variables for which we are getting the best fitness function value, and best fitness, the variable best fitness will tell us what is the actual value of the function at the end of teaching learning based optimization. So, let me now execute this program in the debug mode and put a breakpoint at the very first line, right. So, we would know what is happening in each and every line, we can see the execution, right. So, let me execute this program, right. So, now if we see MATLAB is about to execute the first line, right. So, if we say step, it will execute the first line. So, the command window has got cleared. So, right now if we see, there are some variables present in the workspace, right. So, after this line 2 is executed, we expect that the variables are cleared, right. So, if we do whos now, all the variables have been removed from the workspace, right, because of that second line clear, right. So, this line 5 is supposed to define the lower bound. So, lower bound is defined, line 6 will define the upper bound for us, line 7 will define the variable prop, which is a function handle. So, here we can see that it displays that it is a function handle with the value peer new, right. So, as and when this prop is being called, we will be going, it will go to the peer new function, right. So, if we step in, so NP is defined to be 10, T is defined to be 50, and here if we see, we have defined 10 values, we have defined the vector f which has 10 values, all the values are NaN, right. So, the next step is to determine the length of LB. So, in this case LB, if we see, it has two values. So, D takes a value of 2, right. So, the next step is to generate the population. So, here if we see that repmat function has helped us to generate this 10 members, right. It has 10 rows, 2 columns, right, and all these values are between our lower and upper bound. So, our lower and upper bound are 0 and 10. So, all these values are between 0 and 10, right. So, now this loop will be executed for 10 times because NP is 10, right. So, let me just do step in this time, right. So, as we can see the values x, right, the first member which is 0.08667 and 1.0061 has been sent to this function spear new. It has been sent to spear new despite us calling prob, but we have defined that prob is nothing but spear new. So, it comes into this, right, and if we say step, it calculates the f value, right, f value is 1.7633, and then if we say step in, it comes back over here, right. So, this loop is going to be executed 10 times, right. So, that we can see, right. So, this loop will be executed 10 times, every time a value is returned, right, and it is stored in the appropriate location of f, right. So, this loop is now over, right. So, as of now what we have done is we have created 10 population members, evaluated its fitness using the function x1 square plus x2 square. Now, we will be executing this iteration loop, right. So, initially t will be 1, right. So, the value of t, you can just place your cursor on the variable name and you can see the value. So, t is 1 and this is going to be executed np times, right. So, let me step in over here, right. So, I is equal to 1 in this case, right. So, mean of the population, we need to determine the mean of the population. So, let me see that. So, this is the mean of this particular population, right. The population which we generated is here, right. So, the mean of this population is calculated and stored in the variable x mean, right. So, that is done. Now, if we see the minimum value of f, in this case is located at 1, right. So, what we will expect here is int to be 1, right. Let us see if that is happening, right. Yes, int is 1 because the minimum value of f is located in that particular location, right. So, let us do this thing. So, the value the solution corresponding to 1.777633 is the first member, and the first member of the population is 0.8667 and 1.0061. Right. So, that is the teacher. So, we have been able to extract the teacher. So, TF, if we see, we have generated integer which is either 1 or 2, we were supposed to generate an integer which is 1 or 2. So, randomly we have selected TF to be 2, right. So, step again. So, the new solution which we have generated is minus 6.5790 and minus 1.130, right. So, now if we see, both of these variables are violating the lower bound because the lower bound is 0, right. So, line 38 actually takes care of only the upper bound, right. So, after line 38 we do not expect x new to change because it is not violating the upper bound of 10. Line 38 is not going to have any impact on this particular solution. If it had violated a upper bound, obviously line 38 would have taken care and brought the variables value of the variables back to the upper bound. So, in this case line 38 will not change the decision variable, the values of the decision variable. So, line 39 we are checking with the lower bound. So, minus 6.5790 and 0, which is the maximum. So, 0 is the maximum. So, both of these variables will be replaced with a value of 0, right. So, x new is 0. So, now we have a new solution. We need to calculate the value of the objective function. So, if we step in, since I had clicked on step and not on step in, it did not show us going into the function spear new, but it did use that spear new function and calculated the value of f new, right. So, f of I is 1.7633 because I is 1. So, we are comparing the value f new with the first solution, right. So, the new solution and the ith solution. Ith solution in this case is the first solution because it is the first solution which is undergoing the teacher phase, right. So, obviously we expect this condition to be satisfied because this is 0 and this is 1.7633, right. So, step. So, now if we see, the first member has been overwritten, right. So, this member which we had 0.8667 1.0061 has been discarded. Discarded in the sense it has been removed from here, and we did not store it elsewhere. So, that is why we say it is discarded, right. So, now if I type fitness f is, so 1.7633. So, the fitness of 00 is not 1.7633 because we have not completed the execution of line 45. Right, line 45 will be executed only when this arrow moves on to the next line. Right now it is ready to execute line 45, right. So, if we execute that, so now it has been replaced, right. So, this completes the greedy selection, right. So, step, right. Now, coming to the learner phase, we need to randomly generate a integer between 1 and NP, right. So, let us see what is the partner it selects. So, it has selected the partner 7. Right. So, the solution 1 and 7. So, right now this condition fails because I is equal to 1, P is equal to 7. So, it does not enter this while loop, right. So, it will come over here. So, now we need to check the fitness of the ith solution, that is the first solution, and the 7th solution, right. So, if we check the fitness of it, obviously the ith solution, which is the first solution, it has a better fitness than the 7th solution. Right. So, if we step, so it goes into this equation, again it finds the difference between those two members, the ith member and the partner, multiplies with the random number, again d random numbers, and that value is added to the current member. So, that will be x new, right. So, x new, so x new happens to be minus 4.8665 and minus 0.4536, right. So, if we step in, right. So, again this line will not alter the solution because they are not violating the upper bound, but the next line will bring it to the lower bound because it was violating the lower bounds, right. Again if we evaluate the fitness, right. So, let me just click on step in. So, since I have clicked on step in, it is showing the solution going into the spear new function. The value of the decision variable will be plugged in the objective function, which is x1 square plus x2 square, and the objective function value is estimated, right. So, step again, now if you see the new solution and the ith solution both are same, right. So, the x new solution is also 0 0 and the pth solution is also 0 0, right. So, here this condition will not be satisfied because the new solution, in this case it happens that the new solution and the ith solution both are same, right. Otherwise it would have done the greedy selection and retained whichever is the better solution. So, this completes the teacher and learner phase for the first member, right. This has to be done for all the 10 members, right. So, if we see, it has come to line 74. So, the next step will go to this for loop, right. So, now I is equal to, now we need to do a teacher phase as well as a learner phase, and then for I equal to 3, I equal to 4, I equal to 5, all the way up to I equal to 10. So, now it is at I equal to 2, right. So, the procedure remains the same, it is going to automatically check everything and then things are going to work out, right. So, let me just click on here line 77, right, and then just click on this continue. So, now it is going to continue till it encounters the another breakpoint, right. So, if I do this, so now if I see the value of t, it is 1. So, it has completed one iteration, right. So, similarly I want it to complete all the iterations. So, if I just now do continue again, right, it will come and stop again. So, it has completed 2 iterations. Now, you can complete all the iterations, right. So, let me just click over remove this breakpoint and then just say continue, right. So, since we had removed the semicolon, it ended up displaying each and every step, right. So, but it ended up displaying each and every step, right. So, now at the end of it, if we see these 3 values, so the best fitness is 0, right, and the best solution is 0 0. So, in this case for this peer function, and the optimal solution itself was at the end of execution, right. So, we get the best fitness to be 0 and that is located at first location, right, and the best solution corresponding to this best fitness function value of 0 is 0 0. So, this function we had written it in a generic way, right. So, let us say if I have a 4 variable problem 0 0 0 with a lower bound of 0 and upper bound of 10, right. So, I just merely need to change lower and upper bound, because wherever I required the values of lower and upper bound, I never use the value such as I use the variable LB and UB. So, for example, here if we see when we are generating a new solution, we are not hard coding these values, we are just taking the value of the variable. So, if we change this, it will automatically get changed over here. So, I do not need to change the rest of the code. Obviously, for those of you who are doing reasonable programming, these are trivial things that you would know, that you keep the data separate from the code, right. But I believe some of you are new to programming, so that is why we are reinforcing on that particular point, right. So, now if I execute this, right, so the best fitness is 0, it is located again at the first index, and the solution corresponding to it is 0 0 0 0. If you see, the search space is small, as in like between 0 to 10. So, let me just make this as minus 100, minus 100, minus 100. Obviously, I could have used minus 100 into ones of 1 comma 4, right, but let me just use this, right. So, now if we execute, so now if you see, the best solution is not exactly 0, right, it is close to 0. Best fitness is the value of best fitness is close to 0. So, at the end of 50 iterations, right, with a population size of 10, right, the solution that we are getting is this one. So, the decision variables are minus 0.4046 into 10 power minus 6, minus 0.1678 into 10 power minus 6, minus 0.6328 into 10 power minus 6, and minus 0.154 into 10 power minus 6, right, and the fitness function corresponding to that is this one. So, these values are permissible, right. So, previously the lower bound was 0, right. So, any value less than 0 was not permissible, but right now our lower bound is minus 100, right. So, all these are within our domains, right. So, this is one function. Again, we have written this code in a generic framework that we can also change the fitness function, right. So, for example, we have here let me use the Rastringen function, right. So, the Rastringen function is given by this. We have previously seen that Rastringen function is also a scalable function. We can use it for 2 variable problem, 3 variable problem and 4 variable problem. So, here we have written in such a way that it is scalable. So, we can just say instead of sphere function, if you had to solve Rastringen function, so all that you need to change is this name of the function, right. Again, the population size, if you want to work with 10 and 50, you do not need to change, but if you want to change the population size and the number of iterations that you want to perform, you can obviously change that. So, now if we execute this, right, so we have best fitness that it obtains after 50 iterations is 2.1014 with this as decision variables 0.0589 minus 0.0319, 1.0159 and 0.0264, right. So, if we convert this lower bound to 0, right, and if we execute this, right. So, in that case it is able to find the best fitness function value, right. So, that completes the implementation of TLBO, right. So, this is a basic code. We have not kept track of what was happening in every iteration. So, we will see that a little bit later, but right now what we have done is we have just implemented the basic version of TLBO, right. So, after this we will see the performance of TLBO. So, it performed 50 iterations. Right now what we did was we just looked at the final solution. So, we can also look at what was the best solution it obtained in every generation, right. So, that will actually help us to see if TLBO was able to improve progressively or if the convergence has been reached, right. So, here we have defined a new variable best fit iter, right. So, the purpose of this variable is to keep track of the best solution obtained in each generation or in each iteration. So, since we are going to perform TLBO for 50 iterations, I am creating t plus 1 locations, and not t locations, because I also want to store the best value before we began the iteration, that is in the 0th iteration or in the initial population what was the best fitness value, that also I intend to store it. So, that is why I am giving t plus 1, and it will have one column, because for every iteration we will have only one value to be stored, right. So, t plus 1 rows for t generation and the 0th generation t plus 1, and since only one value is to be stored every time. So, we have this one column. Just like fitness, this will be a column vector. Fitness stores the fitness of the population in the current iteration, whereas best fit iter stores the best fitness function value in every iteration. So, that is the difference between this f and best fit iter, right. So, this line 25 will help us to determine the best fitness function value in the initial population. So, after generating the initial population over here, right, we have this line min of f. So, it will find out the minimum fitness function value, and it will store in this best fit of iter of 1. Best fit iter of 1, because MATLAB starts indexing from 1, not from 0, right. So, that is why the first location is used to store the best fitness in the 0th iteration or the initial population. And then we have one more line over here, right. So, at the end of this population loop, right. So, the population loop begins here and it ends over here, right. So, at the end of the population loop, we find out what is the minimum fitness function value in that particular iteration, right, and store it in best fit iter of t plus 1. T plus 1, because we have already consumed the first location over here, right. The 0th population we have done. When we are in the first iteration, we need to save the value in the second location of best fit iter, because the first location has already been occupied, right. So, even though if we run for 50 iterations, best fit iter will have 51 values, including the initial population, because it also includes the initial population. So, we find out the minimum of the fitness function value and store it in this. This statement will help us display the progress in every iteration, right. So, DISP is a inbuilt MATLAB function to display something on the command window, right. Whatever is there within the single quotes will be displayed as it is. So, I want MATLAB to display the word iteration, right. So, iteration, and then I require it to display the iteration number, the corresponding iteration number, which is actually t, and then I want it to display this full colon best fitness is equal to as it is, right. So, it is given in single colon, and then again we use the num2 string function, right, to convert this value, this number. So, best fit iter of t plus 1 is going to be a number. So, I will convert it into a string so as to use it with the display statement. So, this value is given to num2 string, right. So, it will convert into a string, and since all of this are in between the square brackets, it will concatenate all the strings, right, and that is given to the display statement. So, this will display the best fitness function value in every iteration. So, if I now run this, we will be able to see the progress in each iteration. So, iteration 1, the best fitness function value was 6.3941. In the second iteration itself, it was able to substantially improve 0.048027. In the third iteration, the best fitness function value was 0.0011046, and subsequently it obtained the value of fitness with 0, and then it remained at that particular solution, right. So, this shows the progress of the fitness function value with respect to the iteration, right. So, this gives a better picture as to what is happening in the algorithm, right. So, let us say the lower bound was minus 100, minus 100, and it was a 4 variable problem, right, and the upper bound was 100. So, if we run this, here we can see that initially it started with a solution of 3053.6172 in iteration 1, that was the best fitness obtained in iteration 1, and then progressively it decreased that till it reached 3.4788 into 10 power minus 16, and that at that iteration we had exhausted the number of permissible iterations, right. So, it had to stop over there, right. So, this way we can actually analyze the performance of the algorithm, right. So, now we can also plot this, right. So, instead of having to every time look at this values and analyze, if we had plotted it, our analysis would have been easier. Right. So, in this case, in addition to displaying this, we also plot, right. So, you might have used the function subplot, right. If you have not used subplot, you can quickly do a help subplot and learn the features of subplot. So, here what we are going to do is, we are going to divide the figure, the plot window, into one row and two columns, right. So, that particular figure is going to contain two plots, right, and the first plot is indicated by this position 1 and the second plot will be indicated by the position 2. So, what we are going to do is, we are going to plot first time in the first position, we are going to plot, right. On the x axis we are going to have iterations, right. So, and we also want to include the initial population, right. So, we give 0 to t, right. If you had given 1 to t, then we would have only analyzed what is happening from the first iteration. We may not know what was the best solution in the initial population, right, even before we began TLBO. So, that is why we include this 0, and best fit iter, as we know, has all the fitness function value, best fitness function value in every iteration. Then we add x label and y label, right. X label is iteration and y label is best fitness value, right. Similarly, in the second plot, the x and y axis are same, it is just that it is a semi-log plot with the y axis in the logarithmic scale, right. So, that will help us to better analyze the convergence, right. So, if we run this now, so these are the two plots, right. So, the x axis is iteration, let us just analyze the first plot, right. So, the x axis is iteration and the y axis is the best fitness value and the y axis is the normal scale, right, 0, 2, 4, 6, 8, 10, 12, 12 and 14. So, initially when we started, we can see that it started somewhere close to somewhere about 12, right, and it's the solution, the best fitness function gradually improved, right. This should not be surprising because TLBO, as we discussed, is monotonically converging because we have a greedy selection mechanism. A solution can enter the population only if it has a better fitness function value, right. This the second plot shows the same convergence curve in a semi-log plot. So, the x axis is iteration, it is in the usual scale, the y axis, if you say, it is in a logarithmic scale, right. So, from the first plot it might seem that the algorithm has converged, right, that there is no improvement beyond, let us say 8th or 9th iteration, right. That is because of the scale of the graph, but when we plot in a semi-log plot, we can actually see the performance in a much better way, because even small changes in the fitness function values have been captured because of the semi-log plot, right. So, here if we see, the algorithm has not converged, right, it is still converging. If we increase the number of iterations, it might converge at some point, or we need to increase the number of population. So, this is how we analyze the performance of the algorithm using the convergence curve, right. If the values are drastically varying magnitudes, then we choose to plot the semi-log graphs, right, else the normal graph should be sufficient, right. Now that we have looked into the semi-log plot, right, so every time we run, we will get different values, right. So, this graph would be different. So, here if you see in the command window, right, so this value if you see, every time we run, it will be different, right. That is because it is a stochastic algorithm. So, we need to run it multiple times and do a statistical analysis which we had discussed earlier, right. So, we can implement the multiple runs by converting the script file into a function file. So, this is the function file for TLBO, right. So, we in that file which we showed, we have removed the display statement, right, and we have also removed the convergence plot. All those things can be done in the script file, right. So, this is just, we have in this function file, we just have only the algorithm, all the analysis part we have removed, right, but we also store this to analyze the convergence. We will require this variable, right, because that keeps track of the best fitness function value in every iteration. So, this function is will expect the problem that we want to optimize, the lower and upper bounds, the population size NP and the number of iterations denoted by t, right. So, previously these were defined here itself in the function file. So, that has now been removed and it has been given as input to this function file. So, a user is supposed to provide these detail to use this function TLBO, and what this function file will return is the best solution, the best fitness, best solution as in at the end of the specified number of iteration what was the best solution that was obtained in terms of the decision variable values, and corresponding to these decision variable values what is the fitness function, right, or what is the objective function value, and then the best fit iter variable, the variable best fit iter, which will help us to analyze the convergence, and we are also passing the last population and its corresponding fitness function value, right. So, many a times this analyzing this population can give us further insights into selecting an appropriate solution, right. So, we return this population as well as its corresponding fitness function. Now that we have this function file, we can write a script file which makes use of this function file, right. So, let us go over here, and so this is the script file with which we will be calling the function TLBO, right. So, CLC clear, you know, it is to just clear the command window and to clear the MATLAB workspace. So, we are defining the lower bound, upper bound as 100, and the problem is Rosenberg function. We want to optimize the Rosenberg function with these parameter settings for the algorithm, that we want to take a population size of 10 and the number of iterations to be 50. Now that we have these 5 variables, we need to pass it to the function TLBO. So, for the function TLBO, we are passing the variable prob, the lower bound, the upper bound, the class size or the number of members NP, and the T is the number of iterations that we want to perform, right. So, for this algorithm we have given the input, and this is what we are expecting the algorithm to return: the best solution, the best fitness. So, what is the best fitness in every iteration, including the initial population, the final population, and the fitness function corresponding to the final population, right. So, let me just put a semicolon over here, and if we execute this, right, so it does not display anything because we have put a semicolon at the end of every line, right. But if we type whos, it will show the variables which it has in the MATLAB workspace, right. So, here if we look at best fitness, right, so best fitness is 1.8406. So, for the Rosenberg function with 4 decision variables with lower and upper bound as minus 100 and 100, it was able to obtain a solution which has its fitness as 1.8406. So, what is the solution corresponding to this fitness function? That is given in this variable best sol, right. So, this is the best solution it has determined, right. So, we can get the best solution, its corresponding fitness, and then we can also look at the population, right. So, at the end of 50 iteration, this was the population, right. Since the domain was minus 100 and 100, all the variables are within the domain and their corresponding fitness function is given by f. So, for these population members, this is the corresponding fitness. So, the size of this fitness will be 10 cross 1 because we have 10 population members, right. So, this best fit iter will be a 51 cross 1 vector because we had 50 iterations and we also stored the initial population, the best fitness in the initial population, right. So, that is why if we see the best fitter will be 51 cross 1, right. So, now we have, now since that we have TLBO as a function file, we can implement a for loop over here, right, and execute multiple runs and do a statistical analysis, right. We can also now plot the convergence curve for this particular problem 0 to t comma best fit iter. I need to execute this, right. So, here if we see, it is actually starting with a very large value, right. So, 10 power 10 into 10 power 8, right, and then it brings it to 0. So, if you look at it in a semi-log plot, right, So, let me get rid of this. Right. So, here we can see the convergence in a better sense, right. So, the x axis is iteration, I am not putting the x label and y label. So, x axis denotes the iteration. So, initially when it started with a really high value, right, something into 10 power 7, right, and then it brought it to a value closer to 0. So, here we can actually see the performance of TLBO, that it helps us to progressively find solutions which are better. With that we will end this session. Thank you.